Have you ever tackled a huge jigsaw puzzle by breaking it into smaller sections? That's exactly how divide and conquer works in algorithms. Today, we'll see how splitting big problems into bite-sized pieces helps us solve tasks faster and more efficiently, from sorting massive datasets to aligning DNA sequences in bioinformatics. You'll learn the three core steps: divide, conquer, combine. Explore classic examples like merge sort and quicksort, and discover how this strategy powers real-world applications. Ready to master a fundamental design approach? Let's dive in. All right, let's move on to our key question. How does an algorithm behave as the problem size n becomes very large? Here, we're zeroing in on two critical resources: running time and memory usage. On the chart, time is on the vertical axis and problem size n on the horizontal. The black line represents algorithm 1. It climbs steadily, showing nice, predictable linear growth. The blue curve is algorithm 2. At first, it barely moves, almost flat. Then, whoa! It rockets upward and quickly overtakes algorithm 1 as n increases. That dramatic turn really drives home why analyzing an algorithm's scaling behavior is crucial before you pick one for big data. Building on our look at how algorithms scale, let's dive into running time. Here, we introduce the idea of measuring an algorithm's running time by counting the number of instructions executed under the RAM model, but in practice, it's way too complicated to track every single operation. For example, compare these two quadratic running time formulas: Tn equals 2 things squared plus 4n plus 23. Tn equals n squared plus 10,000n plus 8,000. Both are On squared, even though their constants and lower-order terms differ wildly. Down below, you'll find a simple iterative Fibonacci implementation in C. First, we check the base cases. If n is 0 or 1, return 1. Otherwise, we initialize TMP1 equals 0 and TMP2 equals 1, then run a for loop from I equals 2 up to n. Inside that loop, we compute result equals TMP1 plus TMP2, shift TMP1 to TMP2, and TMP2 to result. After the loop finishes, we return the final result. Notice, this loop executes roughly one times, so the running time grows linearly with n. Building on our earlier examples, let's now dive into the heart of asymptotic analysis: Big O notation. Big O gives us a clean way to describe how one function, f of n, grows compared to another, gnn. Formally, we say f of n is OGN if there are positive constants c and n such that for every n is greater than or equal to n, f of n is less than or equal to secf gnn. If you look at the graph, the horizontal axis is our input size n, and the vertical axis shows the function values. The dashed vertical line marks that pivotal threshold, nen. To the right of n, the curve for f of n never crosses above the curve for secaf g of n. That picture really drives home the idea. Beyond a certain point, g of n, up to that constant factor c, serves as a solid upper bound on f of n. In other words, f of n doesn't grow any faster than g of n asymptotically, so we write f of n equals O of gn. Building on that, let's wrap up with some take-home messages. First, constant factors don't matter when we talk about growth rates. It's the highest order term that really counts. As the input size grows, everything else becomes negligible. Now consider any polynomial of degree k. Fn equals bn plus bn plus bn plus b. If we let a equals b, then we can bound Fn by an plus a. Factoring out n and summing up those coefficients gives us something like Cn. In short, any polynomial of degree k belongs to On. Building on our discussion of polynomial growth, let's take a practical look at how these complexities actually behave. On this slide, titled Practical Complexity, we plot 6 common functions as n ranges from 1 to 20. The horizontal axis is n, and the vertical axis shows function values up to 1,000. On the right, you'll find the legend matching each curve. A dark blue diamond for f of n equals n, a pink square for f of n equals log n, a yellow triangle for f of n equals n log n, a light blue X for n squared, a purple star for n cubed, and a red circle for 2 to the power of n. Notice how the logarithm curve barely moves above 0, while the linear line climbs steadily. The n log n curve sits just above that, then n squared takes off more sharply. Around n equals 6 or 7, the n cubed curve shoots upward, and by the time n hits 10, the exponential 2 to the power of n line explodes past all the rest. This visual really drives home why polynomial and especially exponential growth can become impractical as input sizes grow. Now that we've talked about how functions grow in complexity, let's turn to a concrete problem where efficiency really matters, the classic peak-finding problem. Here's the setup. We're given an array of n integers, and our goal is to locate an index, I such that a greater than equals I1 and a greater than equals a plus 1. At the boundaries, it's even simpler. We just check whether a 1 greater than equals a 2 or a greater than equals a 1. Take our first example, an array of length 9. It starts at 3, dips down to 1, then climbs to 4, and up to 7 at position 5 before sliding back down to 1. That 7 is our peak, since it's larger than the 4 on its left and the 6 on its right. In the second example, the values rise steadily from 1 up to 7 at index 7, then fall back to 1. Again, the highest point, 7, is a valid peak because it dominates its immediate neighbors. Now, let's look at a simple peak-finding routine. Algorithm 1. We start at I equals 1 and scan all the way to n, and at each step we ask, is A at least as big as its neighbors? As soon as we find such an element, we return its index as a peak. Of course, in the worst case, we might examine every entry, so this approach runs in O(n) time. Below the code, you'll see 2 example arrays. In the first, the values wiggle, 3, 2, 1, 4, 7, 6, 3, 2, 1. So we hit that peak of 7 right in the middle. In the second, the sequence rises steadily from 1 up to 7, then falls off, making index 7 the obvious peak. That brings us to the key questions. What exactly is the time complexity of this straightforward method? And can we find a peak even faster? Let's explore whether we can beat O(n). Building on our O(n) approach, let's jump into algorithm 2, divide and conquer. Here's the big idea. We split the problem in half, solve each piece, and combine the results. Step 1? Simply pick the middle element A, 2. That tells us exactly where to cut the array. On the slide, you'll see 2 tables indexed from 1 to 9. In the top table, the values read cool. 3, 2, 1, 4, 7, 6, 3, 2, 1. Fat. A pair of red lines swoops in around the central position 5, where our 7 sits, forming a clear V that marks the left and right subarrays, ready for recursion. Directly beneath, a second table shows what happens as those halves get processed. The first 7 elements emerge as 1, 2, 3, 4, 5, 6, 7, while the final 2, 2 and 1, wait their turn to be split and conquered in the same way. You'll also notice our department header in the corner and the slide number 10 at the bottom. With step 1 locked in, find your middle element. You're all set to dive into the recursive magic of divide and conquer. Building on our divide and conquer framework, let's see how to find a peak in an array with algorithm 2, divide and conquer. First, pick the middle element, A2. Then compare it to its neighbors. If A less than A plus 1, there must be a peak in the right half, so we recurse there. Otherwise, if A less than A1, we recurse on the left half, and if neither comparison holds, that middle element is itself the peak. This gives us the recurrence, T of n equals Tmn/2 plus 1, which solves to O log n time. For example, take this 9-element array. 1, 2, 3, 4, 5, 6, 7, 2, 1. We start at index 5, value 5. See, it's less than 6, so we move right, land on 7 at index 7, and immediately find our peak. Building on that divide and conquer idea, Let's walk through a classic binary search example on a sorted array. Suppose we want to find the number 4 in this list. 1, 3, 4, 6, 7, 8, 10, 13, 14. First, we inspect the middle element, 7. Since 4 is smaller than 7, we know our target lies in the left half, so we discard everything to the right and focus on 1, 3, 4, 6. Next, we pick the middle of that subarray, which is 3. Now 4 is greater than 3, so we eliminate the left side and hone in on 4, 6. Finally, we compare against the middle element there, 6. Because 4 is less than 6, we take the left side one last time, and there it is, 4. This process shows how binary search cuts the search space in half at each step, giving us a fast, efficient lookup. Now that we've seen how binary search zooms in on a target, let's switch gears and look at quicksort in action, thanks to Lou's clear illustration. At the top, you see our initial array, 4, 2, 7, 8, 1, 9, 3, 6, 5. First, we pick 4 as our pivot. It's circled in yellow. Everything less than 4 moves to the left, and everything greater moves to the right, splitting the list into 2 sublists, 2, 1, 3 on the left, and 7, 8, 9, 6, 5 on the right. 1 white. Next, we focus on the left sublist. Here, 2 becomes the pivot, also circled, partitioning that segment into 1 on the left and 3 on the right, each now individually sorted. Meanwhile, on the right sublist, 7 is highlighted as the pivot, which divides it into 6, 5 on the left, and 8, 9 on the right. We keep going. Within 6, 5, we choose 6 as the pivot circled, so 5 ends up on its left with an empty right sublist. And in 8, 9, 8 is the pivot, circled again, and 9 naturally goes to the right. At the bottom, you can see all the final single elements, 1, 3, 5, 6, 8, and 9, each ready to be stitched back together around their pivots. When we reassemble everything, voila, we end up with a fully sorted sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that we've seen quicksort in action, let's turn to merge sort. On the screen, you can see our original list of 7 numbers, 38, 27, 43, 3, 9, 82, and 10. Merge sort begins by splitting this list in half, left and right, until each sublist contains just one element. On the left side, the 4 numbers break down into 38, 27, and 43, 3, and each of those splits further into the single values 38, 27, 43, and 3. Meanwhile, on the right, we divide 9, 82, 10 into 9, 82, and 10, then split 9, 82 into 9 and 82, with 10 already standing alone. Next comes the merging phase. Starting with our smallest sublists, we compare and merge 38 and 27 into 27, 38. Over on the other branch, 43 and 3 become 3, 43. Those 2 sorted pairs then combine to form 3, 27, 38, 43. On the right half, 9 and 82 merge to 9, 82, which then merges with 10 to produce 9, 10, 82. Finally, we take our 2 sorted halves, 3, 27, 38, 43, and 9, 10, 82, and merge them element by element into the fully sorted list, 3, 9, 10, 27, 38, 43, 82. That's merge sort in action. Divide, conquer, and combine, yielding a perfectly ordered sequence. Now that we've seen merge, sort, split, conquer, and combine lists so efficiently, let's turn to another classic divide and conquer challenge, finding a 2D peak in an n by n array. Today's practice problem asks us to locate an entry that's at least as large as its 4 neighbors, above, below, left, and right. In other words, inch is greater than or equal to a1, and right is greater than or equal to a plus 1, and right is greater than or equal to a 1, and I is greater than or equal to a plus 1, and right. The brute force approach would check every element in ON squared time. Safe, but slow. Can we do better? Take a look at this sample 4x4 grid. You'll notice that 20 and 30 both qualify as local peaks. The real question is, how fast can we find just one peak without examining every single cell? Let's dive in. Now, as we wrap up, here are our concluding remarks. First, we focus on the worst-case analysis of an algorithm. To capture that, we use big O notation. Constants are important, and it's the highest order term that really counts. And don't forget, divide and conquer shows up everywhere in algorithmic design.